Hello and welcome to the Maths 2 component of the online BSc course on data science. In today's video, we are going to talk about the echelon form. So, the echelon form is a particular form for a matrix, and when the matrix is in this form, we can read off solutions quite easily. So, let's look at let's recall first what is a system of linear equations. So, a general system of m linear equations with n unknowns is like this: a11 x1 plus a12 x2 plus a1n xn is b1, and then all the way up to am1 x1 plus am2 x2 plus amn xn is bm. Okay, so there are n unknowns, which is the xi's, and there are m equations. Yeah, so for each equation we have a constant on the right hand side. So the ith equation, the constant is bi. Okay, we have seen earlier that we can write this in a vector form, in a matrix form, that is. So we consider the m by n matrix A, which is the matrix of coefficients, and x is the vector of unknowns x1, x2, xn, and b is the vector of constants, the column matrix b1, b2, bm. Okay, and then what is a solution? So a solution is an assignment of values for x, so that the equations are satisfied, right. So when you put xi is equal to some particular number, and for each xi I put in a number, and when the equation holds true, that means indeed when you compute a11 times whatever value you have substituted for x1 plus a12 times whatever value you have substituted for x2 plus a1n times whatever value you have substituted for xn is b1, and the same thing happens for all the other equations, then we say that those particular values that we have substituted constitute a solution for x1, x2, xn. Okay. So let us look at the example of this matrix. So we have A is the matrix with first row 1 0 2 and second row 0 1 3. So let us see how we can find out solutions for this. Okay. So here I am going to write down what the corresponding equations are. Of course, here I have not mentioned what the constants are. So let us take the equation Ax equals 0. Okay. So this is called a homogeneous system, which we will study later. Okay. So the corresponding equations are going to be x1 plus 2x3 is 0 and x2 plus 3x3 is 0. Okay. So now typically what do? We try to manipulate around and find values for x1, x2, x3. If you look at this, there is not really much we can do to manipulate this, and the reason is that we can have many solutions. So how do we find solutions? So you can see from these equations that x1 is minus 2x3 and x2 is minus 3x3. Yeah, and that is all that we need in order to get a solution. Yeah, so whenever we substitute a value for x1 which is negative 2 times the value for x3 and x2 which is negative 3 times the value for x3, we get a solution. So you can put x3 equals some constant c, and then let us say I take x3 equals 5, right. So if x3 is 5, then to get my solution, what I can do is I can put x1 is minus 10 and x2 is minus 15, and indeed the one possible solution then is x is equal to minus 10, minus 15 and 5. Yeah. So 5 was an arbitrary choice for x3. I could have used some other number. So for example, if I use x3 is c, then I get x1 is minus 2c and x2 is minus 3c. So really the set of solutions for this, we can write this as minus 2c, minus 3c and c, where c can be any real number, right. So we can have c is 5, c is 20, c is 1 million, whatever you want. Yeah, and all of these, for each value of c we will get a solution. Yeah. So we have infinitely many solutions, that is the first thing we observe. and not only that, we in fact see that we can get all these solutions in a very particular way. We can really do this for any b. So, if you carefully observe what we did, instead of Ax is 0, if we had Ax is b, we can obtain solutions for Ax is b as well. Maybe I will describe this very fast. So, for Ax is b, what do we do? For Ax is b, what we do is we write down again the same set of equations. The equations are x1 plus 2x3 is b1 and x2 plus 3x3 is b2, and from here we can move x3 to the other side, and then whatever value of x3 we have, we can read off the values of x1 and x2, and each time we will get a solution. So, again we have an infinite number of solutions. Okay. So, there was something particularly easy about this matrix. Yeah, we could read off all the solutions not only to Ax is 0, but Ax is b for any b. Okay. So, matrices of this form have a particular there is a name for this form. It is called the row echelon form, and that is what we are going to study in this video. Okay. So, when is it called when is it said to be in row echelon form? So, it is said to be in row echelon form if the first non-zero element in each row called the leading entry is 1. So, whenever you have a row and it is a non-zero row, so you could have 0 rows of course. If it is a non-zero row, then there will be a first element which is non-zero as you move from left to right, and the first such one has to be 1. The next axiom for the row echelon form is that each leading entry is in a column which is to the right of the leading entry in the previous row. Okay. So, like you saw in the previous example, in the first row the 1 was in the 1/1th place, in the second row the 1 was in the 2/2th place. So, if you consider the second column and you ask or rather you consider the second row and you ask where is the leading entry, which is the first one that you have, it is in the second column, and that is to the right of the leading entry in the previous column, which was in the first row. Okay. So, broadly speaking, you have to go downwards and to the right like this. The ones have to be like this. Okay. Let us look at the next requirement. So, rows with all 0 elements. So, if there are rows which are entirely 0, then they must lie at the bottom of the matrix, they must come at the end. Okay. So, they must be below those rows which have a non-zero element. Okay. So, these three are the requirements for a matrix to be in row echelon form. Okay. And then if you want the matrix to have one further property, which is the following, that for a non-zero row, if you look at the leading entry, yeah, you look at that first one that you have, and then you look at the column in which the entire column. So, already the requirement that the second requirement that each leading entry is in the column to the right tells you that below this one everything is 0. Yeah, you can't have anything non-zero below this one, but you could have non-zero entries above this one. So, we call it, we say it is in the reduced row echelon form if the entries above that leading one are 0. Okay. So, the previous example that we had, which was 1 0 2 and 0 1 3, this is indeed in reduced row echelon form. So, first of all, it is in row echelon form. Let us check that. So, the first non-zero element of each row is a 1. Indeed, that is the case, because what is the first non-zero element in each row? Well, this is the first non-zero element, this is the first non-zero element, and both of them are 1s. And then the second requirement is that if you have a leading entry, you look at the column, and all the leading entries in rows before that must be to its before it, right. So, this one over here, this is in the second column. So, if you look at the previous row, the one is in the first column. Okay, so that's okay, that's exactly what we want. Okay, so these yeah, so this is satisfied, and then this is satisfied, and rows with all 0 elements, well, there is no such row, so this is satisfied. And now let us talk about reduced row echelon form. So it says if you take these ones, then the entire column other than that one is 0. Indeed, below this, the first one, there is a 0, and above the second one there is a 0. So that is also satisfied. So this is also satisfied. Okay, great. So we have seen that in our previous example indeed satisfied this. So it was in the reduced row echelon form, and we could read off the solutions to Ax equals b very easily. Okay. So let us do another example. So here is a matrix which is in row echelon form. So the first in each non-zero row, so all 3 rows are non-zero. The first non-zero term is indeed 1. Is that the case? Indeed, that is the case. 1, 1 and 1. And then whenever you have a leading term, so you have this 1 over here. This is in the 4th column. So the ones which are in the previous columns, so the one in the previous column, it is before this. Okay, it is in the 3rd column. So that matches out. And then the one above this is in the 1st column. So that matches out. Okay. So basically your ones have to sort of go diagonally, but like this, not there can't be a 1 below a 1 or 1 to the below and left. It has to be below and right. Okay. So this is in reduced echelon form. So let us ask, is it in row this is in row echelon form, is it in reduced row echelon form? So for it to be in reduced row echelon form, for the leading terms we have to look at the columns and ask, are all the other entries 0? Well, that is certainly not the case over here, because here is a non-zero entry, here is a non-zero entry, here is a non-zero entry. So this is not in reduced row echelon form, this is in row echelon form. Okay. So let us look at another example, and we can do the same analysis for the second example. In fact, these matrices look very similar, and there is a way of going from one to the other, which we are going to study in the next video. So let us look at this matrix over here. Is this in row echelon form? Well, certainly all the leading terms are 1, all the ones which are leading terms come to the right of the ones which are in the previous rows, and there is no non-zero row. So the third axiom is requirement is satisfied easily. But this has a further property that not only is it in row echelon form, it is in reduced row echelon form, because now these entries over here are indeed zeros, and that is the requirement for reduced row echelon form. Okay. So this matrix is in row echelon form, this matrix, the first one, is in row echelon form, but it is not in reduced row echelon form. And this is in reduced row echelon form. And of course, if it is in reduced row echelon form, it is already in row echelon form, because reduced is a stronger requirement. Okay. So let us do the analysis that we did in the example that we saw earlier in this video. So let us ask, what is the set of solutions for this. So if we want, let us say Ax is 0, A R ref x is 0, what do? We write down again the system of equations. So x1 plus 2x2 is 0, or maybe let us do b. Yeah, let us do the general case, let us do b. Okay, so b, so this is b1, and then x3 is b2, wow, and then x4 is b3, great. So now I want the set of solutions for this. So already we know what is x3 and x4, right? x3 and x4 are fixed, they are b3 and b4. And for x1, what do? Well, I can do what we did before. So I can say x1 is b1 minus 2x2, and then if I choose a value for x2, automatically I can get a solution by substituting that value in this equation and substituting x1 to be that particular number, right. So, if I take x2 to be some c, then I can get x1 to be b1 minus 2c, right. So, this gives me a solution. So, what is the solution? The solution is x is b1 minus 2c, c, b2 and b3. This is my solution for Ax is equal to b, and now whatever value of c you substitute will give you a solution. So, if you take c to be 0 for example, then your solution will be b1 0 b2 b3. If you take c to be 5, let us say, then your solution will be b1 minus 10 5 b2 b3. So, you can see that I can read off solutions for these matrices in this way, and not just some solutions, we can in fact read off all solutions, right. This is the only way we can get solutions for these matrices, and this is how this is the use of the row echelon form or the reduced row echelon form. Okay. So, solutions of Ax is b when A is in reduced row echelon form. Okay. We did not do one small case in the examples, but I will state it here before I talk about the general situation. Okay. So, let Ax is b be a system of linear equations, and suppose A is in reduced row echelon form. Okay. Suppose for some I, the ith row of A is a 0 row, but bi is non-zero. Okay. So, the ith row of A is 0, but the corresponding constant bi is not 0. Okay. Then this system has no solution. Yeah, you can think of why for a second, and if you still can't see why, then here is the reason. So, we can write down the corresponding system of equations, right, and if you write down the system of equations, what will the ith equation look like? The ith equation will look like 0 times x1 plus 0 times x2 plus 0 times xn, because the entire ith row of A is 0. So, the constants, the coefficients there are 0, but on the right hand side you have bi. So, we want that 0 times x1 plus 0 times x2 plus 0 times xn is bi. Now, the left hand side, it does not matter what xi's are, what values you put inside xi's, the left hand side will always evaluate to be 0, right. So, if b is non-zero, then there is no hope of getting a solution, right. Whatever values of x1, x2, xn you take, this equation cannot be satisfied. So, there is no possible solution for this system of equations. Okay. So, the key point is that if a row of A is 0, then the corresponding constant bi must be 0 in order for there to be a solution, otherwise there cannot be a solution, there will not be a solution. Okay. We have seen why. Okay. So, now let us look at the case where such a thing does not happen, right. So, whenever we have 0 rows in A, then the corresponding constants bi are 0. Okay. So, solutions again. So, suppose we have Ax is b and A is in reduced row echelon form. Okay. So, assume that for every 0 row of A, the corresponding entry of b is also 0. So, that means if the ith row of A is 0, then bi is also 0. Okay. Then we can apply the procedure that we saw in the examples that we did before. Okay. So, we are going to give some names here, so that we make this procedure very algorithmic. So, if the ith column has the leading entry of some row, right, there are going to be some columns which have leading entries, right. In our first example where we had 102 and 013, the leading entries were in the first column and the second column respectively. Okay. So, then we will call xi as a dependent variable. So, in that first example, since the leading entries were in columns 1 and 2, x1 and x2 are going to be dependent variables, and if the ith column does not have the leading entry of some row, we call xi an independent variable, right. So, all the other variables are independent variables. So, in that first example, the independent variable is x3. In the second example, the independent variables were x2. So, let us maybe write that down. So, we had 1 0 2 0 1 3. So, here so x 1 and x 2 are dependent and x 3 is independent, and in the second example, well, we had I think 1 2 0 0 and then 0 0 1 0 and then 0 0 0 1. So, here the leading columns, the leading entries are in columns 1, 3 and 4 respectively. So, x 1, x 3, x 4 are dependent variables and x 2 is an independent variable, right. And you saw this reflected in the solutions, yeah, why we are calling it independent. So, if you remember how we solved this, in the first one we took x 3 to be fixed x 3 to be some arbitrary c, and then from there we got what is x 1 and x 2. And similarly, in the second example we fixed x 2 to be some arbitrary c, and then x 1, x 3 and x 4 were fixed. Okay, so that is what we are going to do, assign arbitrary values to the independent variables. And then for a dependent variable, what happens? There is a unique equation in which it occurs, right. So, if you look at the first example, we 1 0 2 and 0 1 3, x 1 occurs exactly in one equation, it occurs in no other equation. Similarly, for the second example, if you look at x 1, it occurs in only one equation, x 3 occurs in only one equation, x 4 occurs in only one equation. So, from those equations we can find out their values. Okay. So, all other variables in that equation are independent variables, right. That is why that is the power of the reduced to echelon form, because all the other in a column with a leading 1, the entries, all the other entries are 0. So, no dependent variables can occur together, right. In a single equation you will have only one dependent variable, if at all. So, all the other equations in that variables in that equation are independent variables, and we have assigned values to them. So, from there I can move them to the right hand side and get the value of the dependent variable, right. And then if we put all these together, the obtained values for x I give a solution to the system, and in fact every solution can be obtained in this way. That is what we saw in the two examples that we did. So, the conclusion here is, if A is in reduced row echelon form, this very easy procedure, it is an algorithm. Let us recall what it is. You find out what are the leading ones, the corresponding columns, the column numbers will tell you what are the dependent variables, all the other ones are the independent variables. For the independent variables you assign arbitrary values and then calculate the values of the dependent variables from the corresponding equations. So, this procedure provides us with all the solutions of A x is equals b. Thank you.